part 2 will usually involve more than one object. So you may need to do the Newton's third law check. So, part 2 questions are more interesting, and I didn't get to, so I want you to do this, even though it is past due, but you can use late pass, and you might be using late pass. So let me do it. And this is, as I think I described this when I was doing part 1. I've actually looked ahead. With my instructor access, I can actually see what question test student will get, and I kept rolling the dice until I got to a question that I haven't done before. So this, when I start, it's guaranteed to be a question that I haven't done before, and I vaguely remember which question it is, but I promise that I haven't really given it a lot of thought since last week, so it's relatively genuine demonstration of how these timed assessments go. So I have my OneNote thing set up so that I can be ready to write stuff there when I'm doing these timed assessments. Usually I need to write. I write enough that I have to scroll, so that's what this OneNote thing is for. So let me get started, and it'll be 20 minutes. And again, when I looked ahead, it was one of the more complicated questions. So I will try to go fast because 20 minutes is not a lot of time, even for me. If I waste too much time talking, then I might run out of time. So let me start. So this is the question. This question, by the way, comes from, wait, I thought I had a different question. Let's hope this is not one of the questions I have done. So, consider 2 blocks on a level plane. It's the level part that surprised me. I thought I picked the one with the inclined plane. Attached to each other with a string over a pulley attached to the wall. This is seating, coefficient friction. Oh, okay, there's going to be friction on all surfaces. All right, it says suppose mass M is pulled to the left horizontally with some force, assuming both blocks slide. That makes things easier. I can assume it's a kinetic friction. So let me draw free body diagram first. And, where it says describe the forces, it's kind of a hack for getting around the fact that you can only type stuff here. You can't draw diagrams here, but, as long as... So you really should be starting with the free body diagram that you draw. So... my free body diagrams, I have a small block M and big block 2M. And the way I like to approach drawing free body diagrams is thinking of the forces that I have to draw. So for both of these blocks, I know I have to draw gravity because there's always gravity, kinda. And once I've drawn gravity, then I can think about, okay, what other forces should there be so that my net force is in a way that's consistent with my understanding of the setup. Now, I know because I'm pulling block M to the left, it'll be accelerating to the left. And I think I have enough intuition that block 2M should be accelerating to the right with the same magnitude of acceleration. So with that in mind, having just this gravity is problematic. I need a normal force so that I can balance out the gravity and not have a vertical net force. So the question says block M is being pulled to the left, so I must have some sort of leftward, I guess, apply the force. Oh, yeah, they gave us a letter F. So I must have that. So with this small block M, you might think, oh, I'm done with all the forces. I have all the forces I need for leftward acceleration. But you shouldn't be so hasty to say you've drawn all the forces. Look at the picture here. Ask yourself, did you draw all the forces? Hopefully you're looking at this string and realizing, oh, there's probably going to be a tension force here. There are other ways you can get this tension force, but kind of easier to get it now rather than later. And then, keep looking, and you should think about, okay, are there any other forces that I haven't drawn? And as you read the question, like this should stick out, that the fact that the question gave you something about coefficient of friction. and you haven't drawn friction force yet. So that should remind you, oh, I probably should draw a friction force. Think about this setup. I'm pulling M to the left. So the direction of friction force is always so that it prevents the sliding between surfaces. So if M is sliding to the left, then the friction on it must be to the right to oppose it. So I need this friction force F1. Again, I keep asking myself, did I draw all the forces? And after a while, at least when it comes to this block M, it should feel like you've drawn all the forces. When you feel that way, then great, you are done. You can stop there. Let me get to bigger mass, 2M. So it's somehow accelerating to the right, and I need to draw enough forces for that. And staring at it, now there's no applied force on it, but it's still attached to some string, so there must be tension force to the right. And this is a decision point, whether to label these two tension forces the same as in no subscripts, or different. And I guess for most of the questions you will see, they will be the same. And what justifies that they are the same is, it's not stated here. Well, the pulley, when we describe the pulley, we'll usually be saying massless and frictionless. That's what tells you that the tension forces should be the same. Here it doesn't say it, but it's such a common assumption that I think I'm going to assume it to say the tension forces are the same. If they're going to be different, then we haven't been given enough information. So you should be staring at this for a while, asking yourself, did I draw all the forces? You should realize, oh, between all surfaces is mu, so I probably need a friction force, F2, I have an intuition that 2M is going to be sliding to the right. So considering this surface with the bottom, as 2M slides to the right, there must be a leftward friction force kind of preventing that sliding, just not well. So now, as you stare at this diagram, you ask yourself, did I draw all the forces? If your answer is yes, I don't blame you. There's a lot going on. It's easy for people to think, oh, I've drawn all the forces. This is why I've given this extra step a name. Newton's third law check. You have to make sure that all the forces you have drawn are consistent with Newton's third law. That means for every one of these forces, you are asking yourself this question. Is this an internal or external force? If it's an external force, great, you don't have to do anything. You're done. If it's an internal force, then you need to check that there's a reaction force pair on the other body that's exerting that force. That's what makes it an internal force. So let me just go through all the forces. The applied force F, almost all the applied forces are almost always external force. This certainly is. I don't have to do anything. Normal force N1. That's coming from the mass 2M. So this is not an external force. It's an internal force, which means I should have a reaction force pair here. I don't, so I should draw it. So there's N1 downward here. Good. Tension T. This is a tough question. I will say it's an external force. It's a force from this string. If you keep following it, it's really going to be the pulley on which the reaction force is. Pulley is outside my system. So T is external force. I don't need to worry about it. F1, that's another internal force. That's a friction force between M and 2M. So it's coming from 2M, which means I need to draw a leftward. Right one. Yeah. So on 2M, it's leftward. Yeah. So there is opposite and equal force F1. That's a reaction force pair to that. Okay, done with F1. And mg, gravity, that's an external force. And I guess if you thoroughly checked one body, then the other one should be all done. But let's just double check. N2, this is force from the bottom surface. That's external. Good. T, it's again, the reaction force is going to be on the pulley, external. That's why these two tension forces are not opposite, because they're not really action-reaction force pairs here. F2, it's coming from the bottom surface. The external, gravity, external, good. The other two forces were already internal. I had to draw them to make sure we obey Newton's third law. So those are all my forces. How am I doing on time? This took a lot of time, but I do say the first step in the standard strategy, which is what this was, is the step that should take you the most time, most care, most creativity. So let me so forces. M has 1, 2, 3, 4, 5 forces, 5 forces. F, N1, T, F1, and NG directions and additional descriptions in attached work. Who has 1, 2, 3, 4, 5, 6 forces. F2, F1, N2, T, N1, and 2NG directions and descriptions in attached work. This is really a bare answer. I'm just trying to go faster. The main thing I require is that there's something in your answer that has that I can tie to your attached work. That's really the main thing I need, so that Okay, find the minimum magnitude of force F needed to make both blocks slide. Okay. So I think what that means is that minimum, you do need to kind of think through to figure out what that means. This imposes some sort of a quantitative condition. And I think what that means, I need to go faster, that's why I'm not rambling on. Acceleration must be approaching zero. So for the purpose of setting up my equations, I'm going to set up so that my acceleration is equal to zero, having approached zero. So I've done my standard strategy, step number 1 here. I need to do step number 2, define axis along the direction of acceleration. So I'm going to actually have 2 different axes. Positive x and positive y defined this way for m, and positive x and positive y defined the other way for 2m. So that acceleration in both cases is in the positive x direction. This particular way of doing things, it limits how many sign errors you can make. Step number 3, we don't really have to do it. It's the components. It's all along the axis for this simple question. Simple but complicated. And I need to write down Newton's second law equations. Net force is equal to mass times acceleration for each object, each dimension. So I'm going to be writing down 4 equations. Let me do that. So net force on block M in the x direction, apply the force F minus T minus F1, that's all the forces, is equal to MA. Net force on small block M in the y direction, N1 minus mg is equal to 0, no acceleration in that direction. Net force on 2m in the x direction, start with the tension in the positive direction, minus the 2 friction forces, F1 minus F2 is equal to 2ma. And I'm just, looking at this diagram and basically copying information over for this Newton's second law equation. Net force on 2m in the y direction, N2 upward, minus N1 downward, minus 2mg, that's all the forces, is equal to 0. That's the end of standard strategy. At this point, I count my equations and my unknowns. Let's count my unknowns first. I'm looking for F, so my F is unknown. Tension is unknown. Friction force is unknown. That's not good. Acceleration. I should have said acceleration is 0 from this condition. So my acceleration is known. It's 0. N1 is unknown. Okay, 4 so far. Making me nervous. T is unknown, but I already counted it. Don't have to count it again. F1 unknown, but already counted it. F2 is unknown. 5 unknowns. A is known. This is 0. N2 is unknown. That's a 6 unknown so far. So I have 6 unknowns and only 1, 2, 3, 4 equations. And hopefully by this time, you kind of know what the other 2 equations are. those are the equations involving these friction forces. So let's just write those as equations 5 and 6. So F1 as a kinetic friction force should be equal to mu times N1, and F2 should be equal to mu times N2. And in the interest of time, let me just plug this in, and let me just do a couple things kind of all together to save me a little bit of time. Equations 2 and 4, I'm going to solve them for N1 is equal to mg. And plugging this in and solving for N2, I get N2 is equal to 2mg plus mg, so 3mg. So I'm going to use these expressions with the equations 5 and 6 to plug in these expressions into equations 1 and 4. So doing that, all in my head in the interest of time, 1 prime and 4 prime give you these two equations, which are really the meaty part of the equation that you are supposed to be solving. F minus T minus mu mg is equal to 0. That's equation 1 prime coming from equation 1. Equation 4 prime is, sorry, not 4 prime, 3 prime. What happens when I go too fast? Equation 3 prime, coming from equation 3, is equal to T minus F1, that's mu mg, minus F2, that's mu times 2mg, is equal to 0. So now at this point in the step, I have 1, 2 equations and only 2 remaining unknowns, F and T. So I just eliminate T, solve for F. So I think the easiest way to do it is I can solve this equation for T. In fact, it's simple enough to do in my head. T is equal to 3 mu mg. Plugging that into equation 1 prime, I get yeah, let me just do it slowly. F, not solve for F yet. F minus 3 mu mg minus mu mg is equal to 0. So I get F is equal to moving these two terms over and combining 4 mu mg. And I guess that makes sense. If the friction coefficient is 0, it should take me basically 0 force to make them barely slide. So I think that makes sense. So yeah, so F is equal to 4 times mu times m times g. Work attached. Yeah, I think that makes sense. I'm just doing a quick sanity check, checking my time. Yeah. All right, what is the tension in the string? Oh, I can just, I already found it actually in the process. T is equal to 3 times mu times m times g. By the way, if you forgot any of these reaction forces, you will have a less tension. That's where your mistake will show up. Complete to see if you have time. Yeah, I think the fact that I'm running out of time is the reason why this is an extra part that won't be graded against you. Imagine the minimum force found is being applied to mass 2m, pulling it to the left. Oh, all right. I will fix that typo. That should not be backticked. All right. Can I? Yeah, I think so I will likely run out of time. When I do run out of time, I'll just, finish this part D and, have it completed for the sake of having something that I can refer to later. So let me start by, I'm just going to copy it over and just, make the changes that I need to make. So the number 1 change is, I guess, the directions in which these object will accelerate will change. Block 2m is the one that's gonna now accelerate to the left. So let me move this over here. And as block 2m accelerates to the left, it'll be pulling block m. So block m will now accelerate to the right. Okay, and let's have some plan to do with these friction forces. The applied force F is now going to be on block 2m. That's the main change you've made. And as that block 2M slides, and this is my block M, this is my block 2M. As block 2M slides to the right, the friction force on it will be to the left to, yeah, so I need to have this F2, no, block 2, no, sorry, block 2M slides to the left. As it slides to the left, the friction force should be to the right. Yeah. So this F2, because the direction will change. So I need to have now F2 pointed to the, let me draw it this way. I don't like this particular style of drawing, but my drawing is so cluttered right now, I can't avoid it. Okay, so that's friction force F2. That's fine. And then F2 is from the let's say that F2 is from the bottom surface, since that's how I've been using F2. And I feel like based on this picture here, the tension force will still be pulling it to the right. So tension I don't really need to change. It'll still be to the right. Okay, I think that's everything for 2M. Let's look at M. And yeah, time has expired. It's doing that. Let me finish D. Actually, relabel this as D. On block M, the tension force will still be the same. Now F1, because it will be accelerating to the right, the F1 will have changed the direction. The friction force preventing it from sliding will be acting to the left. So let's do that. F1, which means the reaction force that we are drawing before, F1 on 2M, the friction force on 2M from the block above, should be now to the right. F1, sorry, this is so cluttered. Okay, so the friction forces have changed the direction. Normal force N1 I don't think will change. Mg I don't think will change. So these reaction forces N1 still the same. I already taken care of the other reaction force F1. So with this change, then I think I kind of want to change my direction of my axis. So for block M, now the positive x-axis will be to the right. For my block 2M, the positive x-axis will now be to the left. Again, so the acceleration is in the direction of the positive axis. So with those changes, let me start by copying these equations over. I feel like a lot of what I've done in earlier parts are still applicable. So I don't think I need to really redo everything wholesale. It's still going to be the case. My acceleration will be going to 0 for the conditions that's specified, just barely starting to slide, the minimum force. So let me actually write my acceleration being 0. That part hasn't changed. Oh, I probably made more work for myself reversing the direction of axis. So I just need to double check with up here, make sure all my forces are in the right direction. This apply the force F, not there anymore, not on the small block M. Tension force is now in the direction of acceleration, so it will be positive. Friction force is still in the direction of negative directions. All right, I'll just leave the minus sign alone. I think we are fine. The vertical direction, nothing's really changed. For the block 2M, now I need to make sure that we add the applied force in the positive direction, so plus F, capital F. Tension force is now in the negative direction, so let's put a minus sign there. Now it's in the negative direction even though the actual direction hasn't changed because my axis has flipped. Friction forces, both F1 and F2 are magically in the negative direction, so I'll leave them alone. And this should still equal 0. Vertical components, nothing's changed. Oh, which means I can actually copy and reuse this work. Me working out the normal forces and the friction force, great, nothing there has changed. I can just reuse them. And let's see here. So plugging this in, let's get the new version of the equations 1 prime and 3 prime. So 1 prime is, it just, so I'm going to solve it for t because that's what I'm going to want to do in the end. So I'll just say t is equal to F1, which will be mu mg. And 3 prime, let me just write down the write down the version with the friction forces plugged in, but nothing else. So it'll be minus t minus mu mg minus, and n2 was 3 mg, so it should be minus 3 mu mg plus f is equal to 0. So I already have tension solved. I can plug that into 3 prime to get minus mu mg minus mu mg minus 3 mu mg plus f is equal to 0. And that's interesting. I get f is equal to 5 mu mg. So it has changed. Don't know if that means it's a mistake or it's just that's what it's supposed to be. So just with a slight bit of a hesitation because I was going fast, doing some steps in my head, there's a small possibility that I made a mistake. So we'll check the answer key to make sure that I didn't make a mistake. By the way, do I have access to answer key? Oh, I have access to answer key now because it's been submitted technically, I think. I'm pretty sure these weren't available while I was still entering. Yeah. That's why I had the setting, that previous setting, that you only have access to answer key after due date, not after submission. That's why I did. So I'll just note that. So I'll just write in my answer to the first donut. What's the time? Can't see the time. My clock says finish it at 11:32 a.m. I ran out of time for this extra part. I get F is equal to 5 times mu times mg with the tension force being T equals mu mg. It feels a little surprising that both F and T are different from before, but maybe that makes sense. Maybe not. If it makes sense, the way I would make sense of it is before pulling the top block, what had to move, what the tension had to pull was the bottom block. So tension was greater, 3 mu mg. Pulling the bottom block, then what the tension now has to pull is the top block, which is lighter, so tension is smaller. I think that I can make more easier sense. Why that should mean the force is greater when you are pulling the bottom block? I don't know. This is the kind of scenario I don't deal with too often, so I will just admit that I don't have a good intuition. If it makes a sense that with the friction force being present, that there is some sort of symmetry between pulling the top block and bottom block. Maybe I'm wrong to expect some sort of symmetry. That's entirely possible, because intuition is really a kind of a summary of your past experiences, and if whatever you're dealing with is something that you don't have a lot of past experience on, then you shouldn't expect to have good intuition. So I don't go around pulling these blocks situated this exact way. So whatever intuition I have, if it's wrong, okay, I wasn't expecting it to be right. All right, so that's my work. Let's save and work and continue. Okay, so 0% until it's manually graded. Let's just double check the answer key to make sure that I didn't make any mistake. And if I made a mistake, then you will at least know that I made a mistake. So 5 forces. Yeah, I think I drew all the forces right. Yeah. Yeah, and tension forces are the same, but I wouldn't identify them as action reaction forces. All looks kind of right. F is equal to 4 mu mg. I did make a mistake. Where did I make a mistake? So I made a mistake earlier. It must be an algebra mistake. Oh, I know what my mistake was. This was the mistake. This should have been 3. So tension here should have been 4. So this should have been 4. This should have been 5. Okay. So yeah, my intuition was surprisingly right. My algebra was wrong. That's what happens when you do things in your head too quickly. I should have really slowed it down, noted that this was 3, and noted it there. So, mea culpa. So actually then, I think what I was expecting with the part D was that the force would be the same, because it feels like they should be the same. So yeah, but the tension force being different makes a total sense. Now, yeah, this was also wrong because I was wrong here. So that should be 4. And for the extra part with all these changes, it makes sense. The tension force is now different because it's pulling a smaller mass. But how much force you need, the total amount of masses being the same, and kind of the magnitude of friction forces being the same, it makes sense that it's still the same amount of applied force needed to overcome the friction. So yeah, I was definitely wrong here. And so let me do this. Now, if you want to change your work, you can reload the work. There's no real due date on how long it takes for the work to be changed. So you can totally do this. You can, just like change your work, now I'm not going to do that. I'm going to do it in an honest way. As in, I'll just say, and then seeing the answer key, I see that I made an algebra mistake in B when I wrote down the expression for F2. Oops. You can, of course, make other kinds of changes. 2 things. One, the more important thing, like it doesn't affect anything, so why would you cheat? Do anything dishonest on things that don't matter. So don't do that. That's 1. 2, it timestamps when you last changed something. So for those of you who are completing this before our group review of timed assessment, you couldn't do what I was doing, look at the answer key until the due date ran out. So the serious discrepancy on the time here and your actual submission time up here will be an indication, hey, what were you doing changing your work, a day after the fact? That's 1. And 2, for those of you who are doing this late, then, I know you had access to answer key. So after submission, so like your work, attached the work, especially means less, to the extent that it means anything. I think I did tell you at the group review of timed assessment session what's going to happen with all this stuff. So, so none of this actually matters. It's all practice.